Imagine the universe of molecules, tiny structures dancing to the laws of physics. Most are content in their symmetrical forms. They exist in states of relative calm and balance, but some molecules, under specific conditions, experience a kind of restlessness. A subtle shiver runs through their framework. This is not random chaos. It is a precise adjustment, a response to an internal energetic imperative. This fascinating phenomenon is known as the Jahn-Teller distortion. It's a story about how molecules seek their most stable, lowest energy state, even if it means breaking perfect symmetry. It's a beautiful fundamental principle at play. The Jahn-Teller theorem, first proposed by Hermann Jahn and Edward Teller in 1937, is a cornerstone in understanding molecular behavior. It tells us something profound. It states that any nonlinear molecule with a spatially degenerate electronic ground state will undergo a distortion. This distortion lowers its symmetry. It also removes the degeneracy, and most importantly, it lowers the overall energy of the molecule. Think of it like a perfectly balanced object. If it has multiple ways to be balanced equally well, degeneracy, it might just decide to tip slightly to one side to find an even more comfortable, unique position. This concept might sound abstract, like a whisper from the quantum realm, yet its effects are very real and observable. They shape the structures of molecules. They influence their colors, their magnetism, and how they react with other molecules. Understanding Jahn-Teller distortion opens a window into the intricate behaviors of matter at its most fundamental level. It's like discovering a hidden rule in the cosmic game of chemistry. This rule dictates how certain players move and interact, leading to the diverse world of substances we see around us and within us. So, prepare to journey into this microscopic drama. We will explore why this distortion happens. We will see how it manifests in different ways. We will look at the molecules that are famous for showcasing this effect. And we will uncover the far-reaching consequences of this subtle yet powerful molecular adjustment. The universe is full of such elegant solutions to energetic puzzles. The Jahn-Teller effect is one of the most compelling examples within the realm of chemistry, revealing the dynamic nature of even the smallest bits of our cosmos. At the heart of the Jahn-Teller distortion lies a concept called electronic degeneracy. Imagine an electron in a molecule. It occupies an energy level like a step on a ladder. Sometimes a molecule has multiple electronic states, multiple steps that are at the exact same energy level. This is degeneracy. It's like having several rooms available on the same floor of a hotel, all equally good. For a nonlinear molecule, if this degeneracy occurs in its ground state, its most stable default electronic configuration, then nature says this won't do. There's an inherent instability. Why is this degeneracy a problem for the molecule? Think of it from the molecule's perspective. It's always seeking the lowest possible energy state. This is a fundamental drive in the universe, from galaxies forming to atoms bonding. If there are multiple ways for electrons to be arranged with the exact same energy, the molecule is in a precarious position. It's like being perfectly balanced on a pinpoint. The slightest nudge, the slightest internal vibration can cause it to settle into a new, slightly different configuration. This new configuration will have a lower energy. The Jahn-Teller theorem mathematically predicts this outcome. It doesn't just say a distortion happened, it says it happened. The molecule will spontaneously distort its geometry. This distortion breaks the original symmetry. By breaking the symmetry, those previously equal energy levels, the degenerate states, split. One or more will become lower in energy, and others might become higher. The electrons will then occupy these newly created lower energy states. The overall energy of the molecule is reduced and stability is achieved. It's a clever trick molecules use. So the trigger is this specific kind of electronic restlessness, a degenerate ground state in a non-linear molecule. The molecule itself finds a way to resolve this energetic ambiguity. It contorts, it stretches, it compresses bonds. It does whatever it takes to break that perfect symmetry that led to the degeneracy in the first place. This relentless pursuit of a lower energy state is what makes the Jahn-Teller effect such a powerful and predictable force in the chemical world, a subtle dance towards ultimate molecular comfort. Not every molecule in the cosmos undergoes a Jahn-Teller distortion. There are specific prerequisites, strict conditions that must be met. The first, as we've seen, is the molecule must be non-linear. Think of a straight line like carbon dioxide. Linear molecules have their own rules and often don't exhibit this particular effect in the same way. The Jahn-Teller theorem specifically applies to molecules with more complex three-dimensional shapes, bent, pyramidal, octahedral, and so on. These shapes offer more ways to distort. The second crucial condition is the presence of electronic degeneracy in the ground state. This is key. If the ground state is non-degenerate, meaning there's only one unique electronic configuration at the lowest energy, then the molecule is already quite stable. It has no energetic incentive to change its shape. It's already found its comfortable niche. The Jahn-Teller effect is a response to an unstable situation caused by having multiple, equally low energy electronic arrangements. Without this specific type of instability, there's no distortion. Consider, for example, a molecule like methane. It has a perfectly tetrahedral symmetry. Its ground electronic state is non-degenerate. Therefore, methane does not exhibit a Jahn-Teller distortion. It's quite happy in its symmetrical form. But take an octahedral complex of copper 3, which often has a degenerate ground state. Here, the conditions are ripe. The molecule will inevitably distort to lift this degeneracy and achieve a lower energy. The presence or absence of this electronic degeneracy is the critical deciding factor. So, the universe isn't just randomly making molecules wiggle. There's a precise set of circumstances. The molecule must have some geometric complexity, non-linear, and it must possess this peculiar energetic feature of having multiple identical ground state energy levels. When these conditions align, the stage is set for the Jahn-Teller drama to unfold. It's a testament to the specificity of quantum mechanical rules governing molecular behavior, a subtle filter determining which molecules will dance to this particular energetic tune. When a molecule decides to undergo a Jahn-Teller distortion, the change isn't always the same. We can broadly categorize these distortions into two main types, static and dynamic. Let's first explore the static Jahn-Teller effect. Imagine a molecule choosing a new distorted shape and then sticking with it. This is the essence of a static distortion. The molecule settles into one specific, lower symmetry, lower energy configuration. This distorted geometry is, for all practical purposes, permanent at a given temperature. In a static Jahn-Teller distortion, the energy barrier between different possible distorted shapes is relatively high, or one particular distortion is significantly more stable than others. Think of a ball settling into a deep valley. It's found a comfortable spot and it would take a good amount of energy to push it out and into another valley. So the molecule adopts this specific distorted geometry, and we can observe it directly using experimental techniques like X-ray crystallography. We see different bond lengths where we might have expected them to be equal. This permanently altered shape is not a flaw, it's a feature. The molecule has actively chosen this configuration to achieve maximum stability. For instance, an octahedral complex might elongate along one axis or compress along it. These are two distinct statically distorted possibilities. If the energy saving from this elongation or compression is substantial, the molecule will remain in that state. This gives the molecule new fixed properties as a direct result of its new, less symmetrical but more stable form. The static distortion is like a snapshot of the molecule's solution to its degeneracy problem. It's a fixed outcome, a clear geometrical change that can be measured and characterized. This permanence makes it somewhat easier to study and understand its consequences. The molecule has made its choice, breaking its initial symmetry to find a more energetically favorable existence. It's a decisive move in the molecular world, a commitment to a new distorted identity for the sake of stability. Section 5. The ever-changing form, dynamic Jahn-Teller effects. Now, let's consider the other side of the coin, the dynamic Jahn-Teller effect. This is a more fluid, more elusive phenomenon. Imagine a molecule again, facing that degenerate ground state. It distorts, yes, but instead of settling into one fixed, distorted shape, it rapidly switches between several equivalent distorted configurations. It's like the molecule can't quite decide which specific distortion is best, or the energy barriers between these different distortions are very small, so it samples all of them, constantly shifting. In the dynamic Jahn-Teller effect, the molecule is in perpetual motion, flickering between various distorted geometries. For example, an octahedral complex might elongate along the x-axis, then the y-axis, then the z-axis, and back again, all very quickly. If we try to take a snapshot using techniques that average over time, the molecule might appear to be perfectly symmetrical. It's like a spinning fan. The individual blades are distinct, but when it's spinning fast, it looks like a continuous disk. The underlying distortions are real, but they average out. This rapid interconversion happens when the energy gained by distorting, the Jahn-Teller stabilization energy, is comparable to or smaller than the available thermal energy or 0-point vibrational energy. The molecule has enough energy to easily hop over the small barriers separating the different distorted forms. So while at any given instant the molecule distorted over a longer time scale, it appears to retain its higher undistorted symmetry. This makes dynamic effects trickier to observe directly than static ones, often requiring specialized spectroscopic techniques. The dynamic Jahn-Teller effect shows us that molecular stability isn't always about finding one fixed, perfect shape. Sometimes it's about exploring a landscape of similar energy states. This constant flux has its own set of consequences for the molecule's properties, influencing its reactivity and how it interacts with light. And it's a reminder that the molecular world is not static. It's a realm of constant motion and subtle energetic negotiations, a dance that never truly ends. Section 6. Spotlight on the affected real-world molecular examples. The Jahn-Teller effect isn't just a theoretical curiosity. It's a real phenomenon observed in many chemical compounds. Perhaps the most classic and widely studied examples come from the world of transition metal chemistry, particularly octahedral complexes. Copper-3 complexes are textbook cases. Copper-3 has a D9 electron configuration. In an octahedral field, this configuration leads to a degenerate electronic ground state, specifically an EG state involving the DZ2 and DX2Y2 orbitals. This is a perfect setup for Jahn-Teller distortion. As predicted, octahedral Q-style complexes almost invariably show distortions. Most commonly, they exhibit an elongation along one axis, usually designated the z-axis, resulting in 2 long copper ligand bonds and 4 shorter ones in the equatorial plane. Less commonly, a compression along one axis can occur. This distortion effectively removes the degeneracy of the EG orbitals, lowering the overall energy of the complex. You can see this in the crystal structures of compounds like copper 2I sulfate pentahydrate, where the copper ions are surrounded by water and sulfate ligands in a distorted octahedral arrangement. Another area where Jahn-Teller effects are prominent is in molecules with certain symmetries and electron counts, like the cyclopentadienyl radical C5H50. This organic radical has a 5-fold symmetry and an unpaired electron in a degenerate molecular orbital. As a result, it distorts from a perfect pentagonal shape to a less symmetrical structure to lower its energy. Fullerenes, those fascinating spherical carbon molecules like C60, can also exhibit Jahn-Teller effects when they gain or lose electrons, as this can lead to degenerate electronic states in the resulting ions. These examples, from inorganic coordination chemistry to organic radicals and novel carbon materials, highlight the ubiquity of the Jahn-Teller principle. It's not confined to one small corner of chemistry. Wherever the conditions of nonlinearity in ground state electronic degeneracy are met, nature will find a way to distort the molecule to achieve a more stable state. These distortions are not subtle imperfections, they are fundamental characteristics that define the structure and reactivity of these fascinating molecular species. Section 7. Reshaping reality, consequences for molecular geometry. The most immediate and visually striking consequence of the Jahn-Teller distortion is, of course, the change in molecular geometry. A molecule that, by simple symmetry arguments, you might expect to be perfectly regular in, say, a perfect octahedron or a perfect tetrahedron, suddenly isn't. Bonds that should be equal in length become unequal. Angles that should be identical become different. The molecule literally reshapes itself to find a lower energy configuration. This is a direct physical manifestation of the underlying quantum mechanical principles. Consider again our octahedral Q archin Y complex. Without the Jahn-Teller effect, we predict 6 identical Q ligand bond length. But the distortion leads to, for example, 2 axial bonds being significantly longer than the 4 equatorial bonds. This changes the overall shape from a regular octahedron to a tetragonally distorted octahedron. This isn't just a minor tweak, it can be a substantial structural change. The degree of distortion depends on the strength of the Jahn-Teller coupling, how much energy the molecule saves by distorting. These geometric changes are not just academic, they have real-world implications. The shape of a molecule dictates how it can pack in a crystal, influencing the material's density and other bulk properties. It affects how a molecule can interact with other molecules. For instance, if a receptor site in a biological system is designed for a perfectly symmetrical molecule, a Jahn-Teller distorted version might not fit as well, or it might bind differently, altering biological activity. The subtle dance of atoms leads to tangible differences in the macroscopic world. Furthermore, these distortions can influence the vibrational modes of the molecule. The way a molecule vibrates is intimately linked to its geometry and bond strengths. A Jahn-Teller distortion, by altering bond lengths and angles, will also alter the frequencies at which the molecule vibrates. This can be detected using techniques like infrared or Raman spectroscopy, providing experimental evidence for the distortion even when it's dynamic and harder to see directly with diffraction methods. The molecule's very rhythm changes. Section 8. Altering the aura. Impact on electronic properties. Beyond reshaping the physical structure, the Jahn-Teller distortion profoundly impacts a molecule's electronic properties. Remember, the whole point of the distortion is to remove electronic degeneracy and lower the system's energy. This involves a rearrangement of the electronic energy levels. Orbitals that were once at the same energy level degenerate or split apart. Some move to lower energy, becoming more stable, while others move to higher energy. This splitting has far-reaching consequences for how the molecule behaves. One key impact is on the molecule's spectroscopic properties. The colors of many transition metal complexes, for instance, arise from electrons absorbing light and jumping between d orbitals. The Jahn-Teller effect, by splitting these d orbitals, changes the energy differences between them. This means the molecule will absorb different wavelengths or colors of light than it would if it were perfectly symmetrical. The observed color of the compound can thus be a direct reflection of the Jahn-Teller distortion at play, a visual signature of this quantum dance. Magnetic properties can also be affected. The arrangement of electrons in orbitals and whether they are paired or unpaired determines a molecule's magnetism. By shifting orbital energies, the Jahn-Teller distortion can sometimes lead to changes in the number of unpaired electrons or alter the way their magnetic moments interact. This can influence whether a substance is paramagnetic, attracted to a magnetic field, or diamagnetic, weakly repelled, and the strength of these interactions. The subtle distortion echoes into the magnetic realm. Furthermore, the electronic changes can affect a molecule's reactivity. The energies and shapes of the frontier orbitals, the highest occupied molecular orbital, HOMO, and the lowest unoccupied molecular orbital, LUMO, are critical in determining how a molecule will engage in chemical reactions. Jahn-Teller distortion modifies these frontier orbitals. This can make certain sites on the molecule more or less reactive, or change the pathways through which reactions occur. The molecule's electronic aura is reshaped, altering its chemical personality and its interactions with the rest of the universe. Section 9. The Grand Significance. Why Jahn-Teller resonates through chemistry. The Jahn-Teller distortion, initially a seemingly esoteric concept from the depths of quantum mechanics, holds a profound significance across the vast landscape of chemistry. It's not merely a curious exception to the rules of molecular symmetry. Rather, it is a fundamental principle that helps us understand and predict the behavior of a wide array of chemical systems. Its importance stems from its ability to explain phenomena that would otherwise remain puzzling, offering a deeper insight into the intricate dance between molecular structure, energy, and stability. In material science, understanding Jahn-Teller effects is crucial for designing and interpreting the properties of solids. Many functional materials, including certain types of superconductors, colossal magnetoresistant materials, and battery components, involve transition metal ions that can exhibit Jahn-Teller distortions. These distortions can influence crystal structures, electronic band structures, conductivity, and phase transitions. Harnessing or mitigating these effects can be key to developing new technology with desired functionalities, building the future molecule by molecule. In catalysis, the Jahn-Teller effect can influence the activity and selectivity of catalysts. The distortion of a metal center in a catalytic complex can alter its ability to bind substrates or facilitate chemical transformations. By understanding how these distortions affect the electronic structure and geometry of active sites, chemists can better design more efficient catalysts for important industrial processes. This subtle molecular shift can have large-scale impacts on how we make the things that shape our world, from fuels to pharmaceuticals. Ultimately, the Jahn-Teller theorem is a beautiful illustration of how molecules strive for stability by adapting their very form. It reminds us that symmetry, while often elegant, is not always the most energetically favorable state. The universe, at a molecular level, is dynamic and responsive. This effect provides a critical lens through which we can view and interpret molecular behavior, explaining spectral features, magnetic anomalies, structural peculiarities, and reactivity patterns. It is a testament to the predictive power of quantum theory and a vital tool for chemists exploring the frontiers of matter.